Hello, everyone. Are you all able to hear me? Okay. Yeah, I believe we can begin the workshop now. So, hello everyone, I'm Marcus and I'm like a year one data science student. And together with me are Hui Sing, year two data science, and also Shankar, year three electrical engineering. And we will be conducting the model tuning workshop for you all today. So before we start, let me first run through with you the outline of the workshop. We will first be giving you a brief introduction of deep learning for those who are relatively new to this domain, followed by the introduction of the fashion mist dataset, which we'll be using it later on. And then next, Hui Sing will be going through the various model evaluation methods, and Shankar will be going through the model training and tuning for you all. And at the end, we will end off with a Q&A session also. So what is deep learning? So deep learning is actually a type of machine learning that can process a wider range of data resources and require less processing time by humans, and can often produce more accurate results as compared to the traditional machine learning approaches. So in deep learning, the interconnected layers of the software-based calculators known as neurons will form a neural network. And the network can ingest like a vast amount of like complex data and process it through multiple layers throughout the entire process. So as you can see in the picture over here, you can see like the main difference between like the machine learning and deep learning. So explicitly for deep learning, there is like minimal or even without like human intervention. So that's one thing you can note about deep learning. So as for the types of neural networks, there are many types of neural networks available also, but the main ones are mainly artificial neural networks, ANN, convolutional neural networks, CNN, as well as recurrent neural networks, RNN. So ANN is the simplest type of neural network, and they are used for a wide range of applications such as like image recognition to natural language processing. On the other hand, CNN is a specialized type of neural network which is particularly good at analyzing images and videos. So they work by using filters to extract out features from the data, as well as combining them with other features to sort of make a prediction. And as for RNN, they are a type of neural network that are designed to work with sequential data, such as like time series or text. So they have this unique architecture which allows them to take into account the context of like the previous input when making predictions. So as you can see in this table highlights like the main differences between the three more popular neural networks. So I've also included the link below, which you can access it if you are interested to find out more. So in today's workshop, we will be covering mainly the CNN. So what is CNN? To put it simply, CNN has like 3 layers in total. So convolutional, pooling, as well as a fully connected layer. So essentially, it is a class of neural networks that process data like a grid-like topology. So the convolutional layer is the basic building block of CNN, which carries the main responsibility of the computation. So that's the first layer. Next up, the pooling layer helps to reduce the spatial size of the representation and reduces the number of computations required. So essentially, it helps to speed up the process. And yeah. And lastly, for the fully connected layer, it helps to connect both the layers together and both the layers together to give out the output. So this is just like a rough idea of CNN. And also here are some of the applications of CNN. So be it you can use like X-rays, medical scans to detect health diseases, or even detect like analyze company logo to come up with some like marketing campaign. So these are some like interesting applications of CNN. So next up, we will be introducing to you the fashion mist dataset, which we'll be using it later on in our hands-on workshop. So the fashion mist dataset is a dataset by Zalondo, which is an online retail company which consists of a total of 70,000 datasets. So there are 60,000 training set. There are 60,000 images in the training set, 10,000 in the test set. And there are a total of, and all the images there are being labeled to up to like 10 classes. So as you can see, the classes are being named at the bottom. Yeah. So if you want to see like roughly how the data set look like, you can see this image on the right. So these are the examples of the images that they have in this data set. Okay, so now I will hand over my time to Hui Xing, whereby she'll be going through the model evaluation methods.
Okay, thank you, Marcus. Right. Okay, so let's talk about model evaluation. So now that you've more or less learned how CNN model works, and let's say you already have your model built, which you should have in your code. So that's when model evaluation comes in, where we determine like the performance of your model and what type of metrics you should use. But before that, right, let me do a quick clarification. So I think some of you might have seen like the terms training set, validation set, and test set, right? And you might be wondering like what's the difference between all these three. And then sometimes you even see like only training and test set without validation, right? So let me go through quickly. So a training set is basically the one that you use to train the model. Meanwhile, your validation set is utilized when you tune your parameters, and your test set is purely used to score and report the performance of your model. So if you ever see like a model that doesn't use a validation set, it basically means that they didn't hypertune their model afterwards. So what they train is basically what they get. And the usual split is about 70% to 20% to 10% in this order. But depending on the situation, like let's say if you want to look at error a bit more, you might put 60 to 20 to 20%. Or if your images are like a lot, like about more than 1 million, your split might be about 98% to 1% to 1% instead. Yeah. Next slide. Okay, so let's move on to the different performance metrics. So sometimes you might see this thing at the side. It's basically called a classification report. And then you see there's like precision, recall, F1 score, support. You might be wondering what all these means, right? Because sometimes you might only know what accuracy really means. So I'll be going through all of that. And then on the side, you can see like these learning curves, which are also more of the common graphs that you'll see when you run a CNN model or just any other model as well. Yeah. So for the classification report and some other things like the confusion matrix, I'll be going through all of this. So there's like accuracy, precision, recall, specificity, all that. So I'll be going through all of this one by one. Yeah. So firstly, for the confusion matrix, this is a binary class confusion matrix, and it's probably the one that you guys will see the most often. Usually, if you ever take a data science like intro mod, everything, this is usually what you will see. And basically how you interpret this is by looking at the axis. So above you can see like prediction and then true label. So when someone says something is true positive, like an easy way to understand what they're saying is basically that the thing they predicted as is positive. And then whether or not it is right depends on whether it says true or false. So if I say something is true positive, meaning I predicted it as positive and this is true because the actual label is also positive. So I think it's like an easy way to remember what all of these mean. So like, let's say I predict something as 1, then if it's actually 0 instead, we'll call it false positive, which is the number 8 at the top. So like, if you ever are unsure what this means, you can just look at the axis, and then these 1s and 0 are basically what binary classes mean. So in binary classes, right, we just have 2 main classes, which is just 0 and 1, and this is how we interpret these graphs. But if you have more than one, these 2 classes, right, we will move on to the next part, which is multi-class confusion matrix. It looks a bit more complicated, I know, but it's actually pretty similar, and the way you read it will be very similar as well. So for example, right, for the flower Virginica, I predicted it to be like, I predicted the flower to be Virginica, right, which is at the very, very end, the number 9 at the right bottom right. And then if it actually is also Virginica, which it is, because number 9 is the true label is also Virginica, then we know that this is a true positive. And then you can read it the same way for all the other boxes and numbers as well. Yeah. Okay, so next, accuracy. I think this is something that you'll hear often, and it's the most easy to interpret, right? Because accuracy, yeah, it makes sense. But I'll be talking a bit more about why this isn't always the best method to use, and it's not very representative of the data you have. Okay, but firstly, accuracy is basically the correct predictions divided by all your other predictions. So as we said earlier, right, you have like your true positives plus your true negatives, and then you divide it by all the other rest, all the other numbers and predictions. So this is basically like the percentage of correct predictions for the test data. However, accuracy usually isn't the best metric because it doesn't tell you how well something really predicts. So let's say if I have like a very imbalanced data set, right? And I only have two classes, like soccer and football, for example, and then the number of data sets and size for the soccer is like 99. Meanwhile, the football is like 1. And then if my model predicts everything for soccer, it will still be 99% accuracy, but it isn't able to predict football properly. So that's when other metrics and other things come in. So next slide, please. Okay, so for this is precision. Also, I think it should sound very familiar if you ever took physics in JC or secondary school. So precision is basically the number of true positives divided by all the positive predictions. So it's true positive divided by the sum of true positive and false positive. And if you remember, I said that if we predict something as positive, the back will be positive, and whether or not it's true or false depends on the first letter. So this tells us like how good a positive prediction made by the model is. So this is very important because it ensures we don't classify too many people as positive when they are actually negative. So this depends on what type of model you're using. So let's say the goal of my model is to predict on whether or not someone has a disease. So if I'm predicting a bunch of people as positive, even though they're negative, right, it's going to have pretty severe consequences, right? Because I'm going to be putting people who are not actually diagnosed with the disease through very painful and expensive treatments, and that's not what we want. So depending on what type of goal your model has, you might want to use precision more than other metrics. Okay, so in the next situation, we have recall. So recall is also known as sensitivity, also known as true positive rate. So it's basically your true positive divided by the sum of the true positive plus false negative. So this ensures that all your positive samples are counted for by the model. So this is kind of similar to precision, just that it chooses a different, it chooses to prioritize a different goal. So we're prioritizing things that are actually positive. So if they're positive, we want to be able to ensure that they're actually predicted as positive, right? We don't want to incorrectly predict someone with like that disease and we don't want to predict someone with that disease as negative when they actually do. So it's kind of important to predict and evaluate both your recall and precision when you have a particular model, and depending on which type of goal your model has, you might want to emphasize more on precision or recall. Like, let me give you a quick example maybe. So like, let's say that your model predicts for suicide, right? You would probably it's probably less harmful to intervene with someone who is like not considering suicide, which is your false positive, than to miss those who are actually considering it, which is your false negative. So in this situation, right, you might want to emphasize more and improve your recall more than your precision. Yeah, next slide. Okay, next is specificity. So specificity, also known as selectivity, also known as the true negative rate TNR, is basically your actual negatives divided by your predicted negatives. So it's true negative divided by the sum of your true negatives plus false positive, and it's also equals to 1 minus false positive rate, right? So this basically measures how often your model will give a negative result when the sample data is actually negative, right? And based on the equation, you can see like if you have a low specificity, it might mean that you will have a higher false positive rate because it's 1 minus FPR. So you're going to have more data points be wrongly predicted as positive. Yeah. Okay, F1 scores. F1 score is an interesting one. It's also known as F score, F measure. So as you can see from the formula, right, it accounts for both precision and recall. So it's like 2 multiplied by precision multiplied by recall divided by the sum of precision and recall. So this is important, and it's quite interesting as well because sometimes when we are unsure of whether or not to emphasize recall or to emphasize precision, right, we can actually use F1 score. So it's also quite useful for when you have imbalanced data sets. Because as I mentioned earlier, right, if your test data only has like most of it is like for one class, even if your model constantly predicts the other class, it will still have a very high accuracy rate. So in this situation, you might want to emphasize and look at F1 score a lot more rather than accuracy. Yeah. Okay, so after we learn all this, right? Okay, let's say you have your result and you look at all these reports and your precision and you realize like, why is my model performing so poorly? So there are a lot of other things we can talk about. So this is where I bring in overfitting versus underfitting. So I'm not sure if you all ever heard of this, but if not, let me give like a brief intro to what it means. Okay, so I think the slides are not edited properly, but basically overfitting, right? It means that when your model is fits your training data too closely, this will occur. So like, for example, when the number of epochs are too high, or when you have a small training data size, right, you're going to overfit. So what this means is that you're going to have a very high training accuracy, but when you test your model, you're going to realize that it's actually having a very poor like testing accuracy and doesn't really perform well on your test set. And that's not what we want, because ultimately, if it trains very well, sure, like you have a high training accuracy, but you want to test it out on the real world. And when you get the real world data, you're going to realize that, things aren't predicting as well as you thought. So I think the slide for the underfitting is wrong, but basically underfitting is the opposite of overfitting. It's when you are not training your model well enough. And this can kind of occur when your number of epochs are kind of low, and there are also other variables and similarities to overfitting, because it's just the opposite. And then this basically means that you're going to have a high error rate for both your training and testing, because you didn't train enough, a lot of the features were not captured, and things are not going to work out. Yeah, next slide. Okay, so this is like your training and validation curves. You might also see this probably quite often in like any CNN model or any other models. They'll always plot out like the training and validation accuracy and the loss. So I'm going to tell you how to read this loss and how to tell whether you're overfitting or underfitting based on the curves. Okay, so if you look at this, right, you can kind of see okay, so you can look at training error first, or like, okay, look at validation error. So you can kind of tell when it goes on, right, your error decreases, okay? And then it reaches like a point where it will start to increase again. And this is overfitting, because when you keep training and training, as I mentioned earlier, your training error becomes a lot lower, right? You're overfitting, but your training error is very low, but you'll realize that your validation error starts to increase. And this is not what we want. So we're trying to avoid overfitting, but we're also trying to avoid underfitting by training your model a bit more. So I'm trying to find that sweet spot. So a lot of times we'll look at this curve, we'll try to make sure that your training error is low, but we also want to make sure that we stop the model right before the validation error starts to increase. Next slide. So there are some important details to know, or like how to fix some of your issues. So firstly, from what I mentioned earlier, right, accuracy isn't everything. Your accuracy alone isn't not sufficient to like evaluate the model. And so that's why we bring in a lot of other metrics like precision, recall. And then as I mentioned earlier, like when do you know when to stop, right? If I overfit, like I want to find that sweet spot between underfitting and overfitting. So one thing that we often use is early stopping. So you can actually find this very easily in Keras and other models. It's very easy to use. Basically, it will stop your training process when your improvement stops increasing. So this basically helps to ensure that you don't overfit and you can have a nice optimized model. And number 3, as I mentioned as well, imbalanced data sets. So sometimes your imbalanced data sets will really mess up your metrics like accuracy, because it's not able to tell, your model isn't able to really tell like whether you can't really tell whether your model is able to predict your different classes. So if that situation occurs, you might also have like a pretty poor performance for your other metrics as well. So what you can do is you can reduce this issue by increasing your data set. So you actually have access to more images, you can do that. But if not, if this is all you have, what you can turn to is actually data augmentation. So if you see the image from the right, like the butterflies, like this one image, you can actually process it very easily, and then you're using different packages, and then you can actually get out a lot more images. Like from this one, right, we have like 1, 2, 3, 4, 5, 6, at least 6 different forms. And in fact, the flip and rotate, right, you will flip and rotate like the images in all different directions. So you're going to end up with like, let's say you have 100 images at the start, you might end up with like 500, 600, 700 images, which increases your data set by a lot. And this will improve your performance drastically, especially if you didn't have many data sets in the first place, right? And you can also try to fix imbalanced data sets by changing the class weight. You can do this in sklearn. It's very easy to implement. So basically you want to make your class weights balanced. So class weights, right? For class weights, basically when, as I said, right, when you have like more images for one class rather than the other, your model is basically going to emphasize on the class that has a lot more images instead. But you want to also focus on the class with very little images so that your model is balanced and is able to predict for both accurately. So you can actually change the class weights to balance in sklearn. And lastly is data leakage. So this kind of occurs when you normalize your data. before splitting them into train, test, and validation. So if you ever realize that you actually normalize your data before splitting them into the different sets, right, you're going to realize that it's going to artificially inflate your score because you're actually bringing in information into your model when it shouldn't be there in the first place. So this is not what we should do. So just make sure that you split before you normalize them separately. Yeah. And I think with that, I can pass on to Marcus for the hypertuning portion.
Yes, I saw in the Zoom chat that there's a question, so we will be addressing it during the Q&A later. Yeah. So okay, so now I'll be going through with you like the initial part of the hyperparameter tuning, which is grid and random search. So essentially how this works is like all machine learning models have a set of hyperparameters or arguments that must be specified by the user. So for example, if you were to set like a logistic regression model and you have like different solvers to find like the coefficient to find the best output, right? Each solver will sort of use a different algorithm to find the optimal output, but none of these algorithms are like strictly better than the other. So it is difficult to tell which solver performs the best based on your data set unless you try them all. So this is where hyperparameter tuning comes in. So hyperparameter tuning is nothing but searching for the right set of parameters to achieve high precision and accuracy. Optimizing hyperparameter constitutes to one of like the most trickiest part in building machine learning models because the primary aim of hyperparameter tuning is to find the sweet spot between the model's parameters so that like the best performance is obtained. So to start off, what is grid search? So grid search is essentially like a searching process whereby when performing like the hyperparameter optimization first, we will first need to define like the parameter or like the space. We need to define a parameter space or like a parameter grid, which include the possible set of hyperparameter values that you can use to build the model. For instance, as you can see on the slide, the batch size 4, 8, 16, 32, 64. So essentially the model will test out every single element in that array to find out what is like the optimal output, like the best output. Yeah. So after this entire process, basically grid search will search for like all the possible configurations, and then the model with the best performance will be selected. So this is the main idea for grid search. So next up, there's also another searching method called random search. While grid search look at every possible element, every possible combination of the hyperparameters to find the best model, right? A random search only select and test a random combination of hyperparameters, as you can see in the image on the right. So this technique randomly samples from a grid of hyperparameters instead of conducting an exhaustive search. So one way that the reason why random search could be better than the grid search is because it reduces the computational time. So random search can achieve better results in fewer iterations as compared to grid search. And this is because grid search considers all the possible combinations of hyperparameters, while random search only samples a subset of them. So this means that the random search can explore a larger area of the hyperparameter space in fewer iteration, reducing the computational time. But yeah, so but then again, if you see the pros and cons between like grid search and random search, since random search does not search through every single possibility, right? So it does not guarantee to find the best hyperparameter as compared to grid search. So it ultimately depends on like your overall aim of this project. So overall, while random search can be more efficient and effective for hyperparameter optimization compared to grid search, especially when dealing with large and complex models, you also have to note that there's no like one size fits all solution. And the optimal method for the hyperparameter tuning ultimately depends on the specific problem, data set, or even the model architecture. So now I'll hand over my time to Shankar. Will be sharing more about the model tuning methods before we proceed to the hands-on the code review.
All right, thanks, Marcus. Okay, so far this has been a bit dry, right? Okay, just let me take you through a story now. So let's imagine you're a researcher investigating different mixtures of chemotherapeutic drugs for their ability to kill cancer cells, right? You've narrowed it down to three molecules, basically C1, C2, and C3. Okay, so now you have to evaluate an objective function f of C1, C2, and C3 in this context, which entails conducting the actual experiments in the lab, which requires manpower, equipment, and waiting for hours or days for the cell cultures to grow. Therefore, considering all the possible concentration combinations is not a realistic approach. Instead, you need to begin with a few random drug concentrations, test them, and then use the experimental outcomes to predict the most promising drug combinations to use next. Makes sense, right? All right. Next slide. Okay, so why use Bayesian optimization? Let's define some common terms before we move on to the actual topic. Samples. So a samples means like one example or one vector from the domain, and a search space means the extent of the domain from which samples can be drawn. And the objective function is a function that takes in a sample and returns a cost of that particular sample. And the cost is a numeric score for a sample calculated via the objective function. All right, Bayesian optimization is an approach that uses Bayes' theorem to direct the search in order to find the minimum or maximum of an objective function. It is particularly useful when these evaluations are costly or when when one does not have access to the derivatives or when the problems at hand is non-convex. You can think of example as your calculus when you took in H2 math or in poly, right? Where you can use the second derivative function to calculate the maximum or minimum. Yeah, this is something similar. All right, so now recall that the Bayes theorem is an approach for calculating the conditional probability of an event. For example, P A given B, the bar is meant by given by, which means that if the probability of an event B has occurred, then so that B represents the subsample space. So P A given B is the posterior, given that the probability of A being true, given that B is also true. All right, you can simplify this calculation by removing the normalizing value of PB, which is also known as a marginalization, and describe the conditional probability as a proportional quantity. This is useful as we're not interested in calculating a specific conditional probability, but instead in optimizing a quantity. All right, so this conditional probability that we are calculating is referred to generally as the posterior probability. And the reverse conditional probability, which is at the top, P B of given of A, is referred to as a likelihood. And the marginal probability is referred to as the prior probability. For example, the posterior, it represents everything we know about the objective function. It is an approximation of the objective function and can be used to estimate the cost of different samples that we may want to evaluate. Now, there's two functions that we need to take note when we're using this method of hyperparameter tuning. They are the surrogate function and the acquisition function. Okay, so the surrogate function gives us an estimate of the objective function, which can be used to direct future sampling, while sampling involves careful use of the posterior in a function known as the acquisition function. Next, the acquisition function is a technique by which the posterior is used to select the next samples from the search space. All right, next slide. Okay, so what if we get additional samples, right? Then we need to do the evaluation via the objective function app, which once they've been collected, they're added to the data D, which is just a matrix, and the posterior is then updated. This process is repeated until the extrema of the objective function is located, a good enough result is located, or resources are exhausted. All right, so let me run through just a gist of this Bayesian optimization algorithm. Firstly, we select a sample by optimizing the acquisition function. Next, we evaluate the sample with the objective function. Thirdly, we update the data matrix and in turn the surrogate function as well. And we loop this and we repeat these steps until we get the most optimal X value. All right. So the black, okay, on the left-hand side, you can see a graph. It looks very scary, but I can try to distill it as much as possible. Okay, so the black dots, right, are measurements, the X values, which is basically an input to the Bayesian optimization algorithm. Okay, the black dotted line is the objective function, and the black solid line is our surrogate model of it. The purple shaded area represents the uncertainty of our surrogate model. The green line is the acquisition function, which informs us what point X to sample next. Now, you can see that the green function takes high values corresponding to potentially high values of the objective function. This is because either the prediction is high or the uncertainty is high, which is why they favor regions that already correspond to optimal values or areas that haven't been explored yet. This is also known as the exploitation trade-off. Now, that's quite a mouthful, right? Now, let me relate to something that you're slightly more familiar with. Now, let's say you've played some strategy games like Age of Empires or Command and Conquer. So, initially, we are placed at some part of the map and only the immediate area is visible to us. Thus, we may choose to either sit there and mine any resources, or we can already access and send a scout to explore the invisible part of the map. By exploring the outer layers of the map, we risk meeting the enemy and getting killed, but we may also find some high-value resources such as gold. Right, next slide. Okay, so here are some advantages and disadvantages of Bayesian optimization. The first advantage being the efficient use of resources. Bayesian optimization intelligently selects the most promising set of hyperparameters to evaluate, which allows it to optimize the objective function using a small number of evaluations. This is particularly useful for expensive or time-consuming objective functions. Second, being the versatility, Bayesian optimization can be used with a wide range of objective functions, including those that are non-convex or have multiple local minima. Thirdly, Bayesian optimization uses probabilistic models to make predictions about the objective function values and for new sets of hyperparameters. Now, this allows it to avoid overfitting to the data which can occur with other optimization methods which shall be mentioned later. Okay, so the first disadvantage of Bayesian optimization is that it's computationally expensive. So this means that the probabilistic models used in Bayesian optimization can be computationally expensive to train and evaluate, particularly for large data sets and complex models. Secondly, the choice of acquisition function used in Bayesian optimization can impact the results. Different acquisition functions can lead to different trade-offs between exploration and exploitation, and selecting the right acquisition function can be quite challenging. Okay, thirdly, Bayesian optimization is sensitive to the choice of prior for the probabilistic model. If the prior is misspecified or mislabeled, the results can be suboptimal. Okay, so in summary, Bayesian optimization is a powerful technique used for hyperparameter tuning, and it can be it can be a useful tool for improving the performance of machine learning models. Next slide. Okay, now I shall hand over to Huisin to talk about the gradient descent.
Okay, thank you, Shankar. Right, so gradient descent, basically how it works is that it finds the optimal parameters by minimizing an error function. Okay, and your error function is going to differ for all your different models. So there's going to be a bit of calculus in this, but I'm not going to go through that because actually the implementation for gradient descent in like your CNN model will be very, very simple. But basically, you first initialize your parameter values. So for example, you can start at any random values, and then afterwards you can fix this learning rate. And this learning rate is very important. I'll explain a bit more later, but basically you fix this learning rate first to control like the rate of change for your values for your parameters. And then afterwards, you'll calculate the partial derivative of your error function. So as I mentioned, the error function kind of differs for all different models. So like logistic, it will differ, CNN, it will differ, but you want to calculate your partial derivative with respect to your parameters to keep updating your parameter values. So it's basically like a for loop, right? You keep iterating and iterating and iterating until you reach this convergence point. And what this convergence point is, it could either be where your error function is minimized to a certain threshold that you set, or when it reaches 0. If not, it can be like when you hit the max number of iterations reached. Next slide. So this is like a very nice representation of how gradient descent looks like. So at the very, very bottom, you can treat it as like your convergence point, right? So as you update your values using your learning rate and your partial derivative, you will keep moving forward towards your convergence point. And then this is where your learning rate really comes in very important. So your learning rate cannot be too high because as you see, right, you will keep updating until you reach a certain point. But if your learning rate is very high, it will actually overshoot this convergence point and you will end up diverging and you won't be able to find an optimal solution. And you might think, okay, I can make this smaller, right, my learning rate. But you realize that if your learning rate is too small, it's actually going to take forever to train. So your algorithm will be super slow. And in that situation, you might not even reach your gradient descent before your iteration ends. Next slide. Can we, okay, I'll actually address the chat question in my next few slides, but yeah, don't worry, I'll move on first. So basically, right, as I mentioned, it seems very tough. Like I have to find the calculus, I have to calculate using calculus, the partial derivative, etc. But actually, when you actually build out your code in Python, it's very, very quick. So you see both of this, actually they do kind of like the same thing, just have different loss function, which is like your error function. Basically, right, you want to put in your optimizer. Your optimizer, for example, the one at the bottom is optimizer equals to Adam. So Adam is basically one of the gradient descent variations. Adam is slightly better, okay, not slightly, it's much better than gradient descent because it actually adds momentum. So what this does, right, is, for example, in this chat, right, in chat question from Nigel, they basically said like, what if my surface has, can we assume that surface has only one minimum? Okay, it's not true. So you can actually have different minimas and you might not always end up with that one nice convex curve. So what will happen is that sometimes your gradient descent will end up converging to, a local minima instead of a global minima. So it is still better than other points, but it is not the most optimal because you're not at the global minima. So in this situation, right, Adam comes in very handy and it's one of the more popular optimizer methods. So what it does, it adds momentum such that you can actually overcome this local minima and end up getting at a global minima instead, which is much more optimal. Yeah, so this code is super simple to just add on. I think a lot of machine learning algorithms out there or like code out there, when you see, they most likely also use optimizer equals to Adam because it's just a very popular algorithm. Yeah, next. Right, so now that I mentioned all that, let's talk about the advantages and the disadvantages of gradient descent. So firstly, the good thing is that it doesn't use that much memory. So that's great, right? So, and then there are also a lot of other derivations like stochastic gradient descent, batch gradient descent, and then as I mentioned earlier, right, other than Adam, there are also a lot of other optimizers you can use. But then there are a lot of other disadvantages as well. So your error function must be differentiable. So as I mentioned earlier, right, you must find a partial derivation. So in the situation, right, if you're unable to differentiate your error function, you basically can't carry out gradient descent. And then you must also be convex. If not, there is no minima for you to converge to. And as I mentioned earlier, your state of convergence may not be the most optimal as well. So you might actually converge to a local minima instead. Okay, and then next, so gradient, we keep talking about gradients and like how you differentiate everything, right? So afterwards, you may actually encounter two very large problems, which is exploding gradient and vanishing gradient. So exploding gradient, right, what happens is that your gradients keep increasing and increasing until your algorithm just diverges. Because as I mentioned, like you basically differentiate your error function to kind of update your value. So if this gradient, right, keeps getting larger and larger, you're going to realize that your values will just go haywire and you won't be able to converge at all. Meanwhile, vanishing is the opposite problem. instead of getting larger, your gradients keep getting smaller and smaller and smaller until your parameter values, like, they don't change at all, or they're equals to 0. So nothing changes and you're not able to converge as well. So I think with that, we can actually move on to the code and we can kind of go through some things. Yeah, Marcus, please.
Yeah, sure. We'll be moving on to the coding portion now. So okay, let me go to the code. Yeah. Okay, so yeah, so you guys should be able to access this code in the Google Drive link that you all receive in the email. If not, then feel free to let me know if you all need the link, then we can also bump it in the Zoom chat. So essentially now we'll be going through the more technical portion of this workshop. But just a disclaimer that this is mainly to familiarize yourself with like the concept. So we won't really be delving deep into the logic or like each line of code, but it's so that you guys have like a rough understanding and will remember it for a longer period of time in the event that you'll see it again in the future. Okay, so let's start. So we'll start off by importing like the various libraries such as like pandas, NumPy. But the more important one would be the last two, which is like the TensorFlow Keras model, as well as the different layers. So the dataset we'll be using is this fashion means dataset. So you don't have to download this dataset because we can retrieve it from the Keras API. So just by running this code, you'll be able to download the data from the API itself. So yeah, it won't use up additional space on your desktop. Then you can roughly see the shape of the data frame also, as well as an example. So as you can see, if you run this code over here, right, you'll see an example of each type of what's that? The images in the data set. So for instance, like ankle boot, t-shirt, t-shirt/top. So essentially, similar to what I mentioned earlier, there are 10 classes in total for this data set. So these are just an example of like the first 25 images. So next up, scaling and reshaping. All these will be part of the data pre-processing stage. So essentially, we will scale this value between the range of 0 and 1 so that we'll be able to fit it into our neural network model like more easily. Yeah. So okay, so this is the more important part whereby we covered it in today's workshop, which is the hyper tuning of the model. So I will give you all some time to look through this code and roughly like and you can read the comments also to roughly understand before I go through. Yeah, I'll give you all like 10 seconds to take a glance of it. Oh, reconnect. Okay, so essentially this is a function that uses Keras to build a CNN with the hyperparameters defined by the user. So like here's the breakdown of the code. So essentially it creates a function name called build model. And then the model is created with like the following layers. Remember previously I said there were like 3 layers. Yeah, so in this case, we'll start off by adding a 2D convolutional layer over here. And then we will state the input like arguments inside also, such as like the activation function ReLU, as well as the shape, the input shape. So ultimately, all this depends on the data set that you get. So yeah, you should be able to change all these values too. It's not fixed or restricted. So secondly, we also add another layer to further filter down the images. So and lastly, and we also added a flattened and dense layer. So this is like the rough outline of the model that we created for this workshop. But do note that this is not restricted. There are other possible like combination as well. You can add like more than 2 layers, or like even like 3 layers as well as add in the pooling layer. So this is just a rough example of what you can expect when you create a CNN model. So after creating a model, what we can do is to optimize the model, which is in this case, we can do a random search. So a random search, we can import random search from this Kira tuner. So Kira tuner is basically a library which helps to optimize these processes in just one line of code. So as you can see, creating this tuner for random search, we just need to put in like minimally 2 to 3 arguments. In this case, your model, the objective, which is the metric that you want to focus on that Hui-Xin covered previously. So be it like the accuracy or like the loss accuracy, etc., as well as the number of trials, means like the number of like iterations or run through. So after running through this code, you can see the output below, trial 2 complete. I only put 2 trials because as you can see, the total elapsed time, it takes around 26 minutes, which is quite long. So you can, if you divide by 2, 1 round is approximately 13 minutes in this case. So yeah, so based on like the 2 trials that I conducted, right, the second trial, the value accuracy is only 0.828, whereas the first trial was 0.8999. So which is why this model, this line of code over here tracks down which one is the best accuracy, which one has the best output so far, and it will just ignore like the trial 2. Yeah. So in the event that you want to save the parameters, right, you can use tuner.getTheBestModel and then to save it, as well as view the summary of the model, like the various hyperparameters after you have tuned it. So these are the different layers, as well as the most optimized hyperparameters. Lastly, this portion, the following portion is for the fitting of data. So once you have trained the model already, right, you want to fit the data, you can store it over, you can use model.fit to store the data. And then remember to save it, assign it to a variable history.to, so that you are able to plot this training and loss graph later on. In the event that you don't put history.to, right, your all this code will not, the result will not be saved, and then you have to rerun this again, which takes like half an hour. So you wouldn't want to do that. So remember to assign it to a variable, and then after that you can call history.to to see the results, the individual results of like the loss accuracy, value loss, as well as the validation accuracy. Yeah. So think for this portion, Hui-Xin covered previously, which is the graphs for like the training loss as well as the training accuracy. As you can see, the x-axis is basically the number of epochs, which is like the number of iterations per round. So the number of iterations, as the number of iterations like increases, you can see that the number of like training data loss like decreases, as well as the training accuracy increases, which is something that you should expect when training a model. And to finalize this, we can also do this model.evaluation to calculate the test loss as well as the test accuracy of the model, like after you have fitted it. So as you can see, the final accuracy of this model, it's 0.884, which is not bad, but of course, if you were to tune the hyperparameters even more, such without overfitting the model, then the accuracy will be higher. So this is just the rough outline of the random search. I also included a bonus segment which Shankar covered about the Bayesian optimization. So similarly, you can import the Bayesian optimization library and then put in the various hyperparameters for your based on your data set. Then after that, you can use this line of code to create the Bayesian optimization object and start to search. So essentially, you can see the code is quite similar to the random search also, whereby in terms of the various arguments inside. Yeah. So and after running all this, right, you can see the difference in like the validation accuracy. In this case, it's 0.937 after like 2 runs or so. And in this case, it takes like 17 minutes as compared to the random search, which had the best accuracy of 0.899. So as you can see, for this case, the Bayesian optimization dataset, if the Bayesian optimization library is a much better optimization model as compared to the random search. Yeah, so essentially this is all for the technical portion, and yeah, thank you all for sitting in for the past 1 hour. So we'll open the floor to any Q&A now. Yeah. You may feel free to just type your questions in the chat and we will answer them. Yeah. So what is a good way to choose the number of trials for random search? For example, if we have 10 hyperparameters with range 5 value each, what should be the number of trials? So I wouldn't say there's a explicit, like a specific number as to like, how to say, a specific table whereby, oh, you have like 10 hyperparameters with range 5, you should do like five trials, etc. So ultimately depends on like the computational power that you have and like how much time are you willing to like invest on it. Like, because assuming that you want to make it like super accurate, right? You can choose to run it like you can choose to run it like more than like 20 times or so, but then again, you have to, your computer will be like will be loading for like more than for a couple of hours. So it depends on like it depends on your priority as well as the like the weightage of this like model. Yeah. For Huixing and Shaka, feel free to add on in the event that I'm like, feel free to correct me if I'm like wrong also in any portion. Yeah. Sorry, Nigel, may I clarify what do you mean by where the hyperparameters that you guys were brute forcing over in the code? Missed that part. Is it the number of epochs?
Oh, sorry, there's a typo. I wanted to ask what are the hyperparameters that you guys are brute forcing over, not where.
Oh, what are brute forcing over?
Oh, do you mean what we are finding, like the ones here in the Bayesian optimization, like learning rate dropout, etc.? Is that what you mean?
Like in the, because you guys say random search with the hypergrade thing, right? Means that you randomly choose a value. That value is for what? Is it like number of runs? You randomly choose one and then you see how it works. And then
Yeah, correct. So basically, like for example, the right now on the screen, right, you have learning rate. So as I mentioned, learning rate earlier, right, is like
okay.
yeah, correct. So these are the values that we are trying out. So basically, you want to try out a bunch of values, right? You key in all these values into your hyperparameters, and then afterwards, it will search through all of these different options one by one. So you don't have to manually like iterate through every single combination. So this is what, like for example, grid search does for you.
I see. What about the random search one? Because I didn't see such a hyperparameters dictionary for the random search part of the code.
For the random. For the random search. I think for the random search, you don't have to put in the hyperparameter because this is ultimately like a deep learning model. So it's able to generate the hyperparameter even for this random search, even if you don't include it. But in the event that you want to include it, I believe there's an argument for it also for you to include the hyperparameter in this case.
Okay, thanks.
All right, I think for Joshua, right? I think dropout is in the CNN. I don't think I mentioned it for Bayesian optimization.
Yeah, the dropout is part of my hyperparameter for the Bayesian optimization. So wait, give me a second.
Oh, okay, sorry, my bad. Okay, so like dropout is basically to reduce overfitting lah, so that it's something like regularization. Dropout just basically sets some neurons to zero. So it's just used for prevent the is to prevent the model from overfitting. All right, I think so. To answer Jet's question on the ghost hyperparameters, right? Actually, that's a very valid issue. Okay, so from understanding, right, to avoid this issue, it may be useful to use an acquisition function that can handle missing or irrelevant not relevant hyperparameters. Okay, so like this acquisition function takes into account of the uncertainty in the surrogate model and the constraints on the hyperparameters to select the next set of hyperparameters to evaluate. So yeah. So in short, right, we can place some constraints on the hyperparameters such that the acquisition function can effectively handle the ghost parameter, can handle the ghost hyperparameters and prevent the algorithm from exploring the irrelevant search space. Oh, just broadcasting in
Sorry, Shankar.
Yeah, to address Nigel's question about the build model function, perhaps I can just send this link. So essentially, this is part of like the Keras, like the hyperparameter library. So it essentially takes in the for the choice method, it essentially like choose a value, choose one value among like a predefined set of like the possible values as well. Yeah, it's part of like the library method. Yeah, in the link you can also see the various tuners also. They have like other tuners like hyperband tuner as well as sklearn tuner. So there are like 4 tuners in total in the link that I sent. Yeah. Hi Nicholas. Okay, maybe we'll take this as the last question. So sorry, quick explanation. How is this example of transfer learning, or is it not? For this portion is not transfer learning. I think there might be a mistake in the publicity material whereby we talk about like transfer learning. Yeah, so this portion is we didn't cover transfer learning. So yeah.
Okay, I think for transfer learning, right? In short, you can think of it as using your friend's homework and then changing just a bit here and there, and then like submitting as your own homework. So that's what transfer learning is. Basically, that's it.
For image classification, good ones, I've heard of these two before that I said in the chat, the VGG16 or ResNet 50, like based on my research that I did previously. So I think these are relatively good pre-trained models in the event that you want to explore this area. Yeah. Yeah, sure, no worries. If not, then thanks you all for attending this workshop, and we will be ending the workshop here. Yeah. Okay, thanks for coming, everyone.